This is a lesson on change of state, transferring from solids, liquids, and gases, and phase diagrams. A key component, key idea we have is vapor pressure. Vapor pressure is the additional force of the gas exerting in a sealed container where the rates of condensation and evaporation are equal. In other words, you're forming an equilibrium. So what you have is you have some sort of a liquid in a flask that is stoppered, and you put the liquid in there. You note the pressure in the beginning. Eventually some of this stuff is going to evaporate, and then you're going to reach equilibrium where some of the stuff is going to condense back out. The liquid level is going to lower a little bit, and you're going to find an additional pressure. So that additional pressure above the atmospheric pressure is equal to the vapor pressure. So it's the additional pressure due to the added molecules of gas from the liquid. You can have vapor pressure of a solid too. It's just much less than that. So if the rates of condensation and rates of evaporation are equal, you have an equilibrium. This depends upon, very much so, the temperature. If you have more molecules, if you have more energy, there's more molecules that have enough energy to break that surface tension that we talked about before, and so you're going to have additional force of pressure and the substance. Some organic molecules, very low, they're nonpolar, so they have very high vapor pressure. The water has a very low vapor pressure because they're very strongly attracted to each other. They have a strong intermolecular force. So the substance depends upon the intermolecular force. Weaker the force, the higher the vapor pressure. Temperature, if you have more energy available, more particles have enough energy to break the surface and vaporize. Overcome surface tension. Solids do have vapor pressure. An example of the temperature. Here's the energy needed to vaporize, to break the surface tension. At a low temperature, you have more particles in a distribution curve down here, so you have very few gas particles available. If you raise the temperature, the heel falls off, so you have more particles that can escape. So this is the number of particles, and this is the temperature / energy. If you have, if you heat up a solid, it will undergo a phase change, it will melt, and then if you continue heating it, it will boil. So you can have a heating curve. There's also an associated cooling curve with it. So if you start low temperature, you heat it up, you have a solid, then it levels off, there's no change in temperature as all that energy is going to break the potential energy of the bonds, and then you heat it up, the kinetic energy, the liquid gets warmer until it hits its boiling point, then it levels off. Energy is being added to break the bonds, and then it shoots up. The slope of these lines correspond to the specific energy refers to the amount of energy it needs to warm it up, specific heat of each substance. So this would be the melting point, and this would be the boiling point. You can draw a corresponding cooling curve where it goes down. You can have a cool down substance. If you look at a cooling curve and you're going to a solid, if you look at it very closely, you'll notice that you can get a supercooled solution. They need a little bit of surface or something needs to activate it. So you can get, this is a very small region. It's not very noticeable. If you're doing a cooling curve, this part right here corresponds to that. Very small amount. It just needs some solid to hook onto. Same thing happens on the heating curve. You can have a superheated liquid, and then you cool it down. This you can see in a microwave. If you heat up water in a glass and then you pour some cocoa powder or something in it, it'll foam up really rapidly, even though it's not boiling. This caused some health concerns in the past. People put stuff in it and hot boiling water splashed up all over them. The normal boiling point and melting point, the normal of these is at 1 atmosphere of pressure. If you increase the pressure or decrease the pressure, those boiling points and melting points change. It depends because of the vapor pressure. Boiling occurs when the vapor pressure is equal to the external pressure or the atmospheric pressure. The lower the vapor pressure, the lower the atmospheric pressure, the lower the vapor pressure is, and it will boil at a lower temperature. This is why you have special heating instructions at high altitude thing. Okay, then you can have for a substance, a phase diagram. On a phase diagram, it shows, kind of relating back here to this concept of boiling point equaling vapor atmospheric pressure. You have different regions, and this is going to be one of the objectives. You have temperature on the horizontal axis, pressure on the vertical axis. At very low pressures, very low temperatures, it doesn't have to start at 0, but we're going to do it here. The phase change looks like this, most of them. There are variations. You can have different allotropes or types of things that you have. So you have something like this. At low pressure and high temperature, you have a gas. At low temperature, high pressure, you have a solid. And in between those is a liquid. If you have 1 atmosphere, this will show the normal boiling point and melting point, because when you draw a horizontal line, this point right here at this temperature was the phase change between the solid and the liquid. It's phase change going from solid to a liquid at 1 atmosphere, so that would be the normal melting point. This point right here would be the normal boiling point. The normal boiling point, because you're going from liquid to a gas. If your atmospheric pressure was here, it would not go through the liquid, you would have sublimation going on. So this is sublimation at different temperatures and pressure. This would be melting point, the line of melting points at different temperatures and pressures, and this would be the line of boiling points at different temperatures and pressures. This point right here, A, is the triple point. If you can maintain that pressure and temperature, if you have 10 grams of solid, 10 grams of liquid, and 1 gram of gas, you come back 50 years later, you're going to have 10 grams of solid, 10 points of liquid, and 1 gram of gas. Nothing changes. That's where all three phases are in equilibrium with each other. This point right here, point B, is the critical point. Critical point. Above that temperature, no amount of pressure will cause it to turn into a liquid. So up in this area, there is nothing, and then this is the plasma up here at very high, going on beyond that. So that really doesn't exist. It's just kind of fuzzy. It's a fuzzy line because people can't get that temperatures as we did going there. So we got critical point, triple point, temperatures. Water is unique in that when we curve it, its melting point has a negative slope. So that means if you have a temperature here, if you increase the pressure, it will convert back to a liquid. This explains why ice would float under high pressure. Some people say this is skating, some people say it's a fallacy that under high pressure the skates make the ice melt underneath its skate rim, the metal, and you glide along on a piece of water. It doesn't do that. There are different gases and different things. Every substance has its own little unique thing. Hydrogen would look something like this. Iron probably look something like this. So they got different things. You can have different forms. You can carbon and diamond. You can have a phase diagram for that where you have different allotropes and different things going on. I guess that wouldn't be iron. I guess iron would be something like this. So that'd be iron, because most of iron is solid. No, most iron is, I had it originally right. Iron would look something like this. Most of iron is solid, very little iron is gas. Okay. One wrong. So that is the lesson on changes of state by phase diagrams.